Hello Mario Warriors, hello Harsho, hello Deva, hello Hari, hello Niranjan, welcome Sudarshan, hello Maha, welcome guys, welcome aboard to the next session of your NEET crash course. The Elite crash course is what we call it. I hope I'm audible as well as visible. Hello Emily, nice to see you guys. So in the Elite crash course, I'm going to do all the important chapters of 12th as well as 11th, starting with some important 12th standard chapters because it will be immediately helpful for you in your board preparation and obviously will help you in your NEET preparation. And today's topic is nuclear physics. That's what we're going to do, guys. Now, this is how the Elite crash course works. This is a theory session. There will be maybe 1 or 2 more theory sessions, and then there will be a problem solving session on the previous chapters or whatever theory has been taught. So theory, problems, theory, problems. So 2 or 3 or 4 theory classes and then problem classes. That's how it works. So in this lecture, you will see a lot of concepts, a lot of things right from the basics to the NEET level. And then you'll get additional practice with PYQs and NT-Abhyas material in the problem solving. Okay. So my name is Shreyas, guys. You can also quickly introduce yourself if you are new to the channel. And if you are old, I hope you have smashed the like button. That's my small introduction. You can follow me on Instagram as well. And my dear students, I would love you to subscribe as well as like the videos because it helps in the YouTube algorithm and automatically you will not miss anything because it will come up in the feed and in the notifications. Nice to see all of you. Saravanan is new. Hello Salva Kumari, Vanakam, Vanakam. Obviously I know you, you have been there with me for a long time. Hello Ashika, good evening. So guys, last few days I was not able to take a class because I was in the alumni meet and I met some really interesting people and I had some interesting conversations. I got to know some nice stories. So stay till the end. I will tell you something interesting regarding medical field and doctors. Okay, I'm pretty sure you're all excited the moment you hear story and something which is interesting related to whatever you are studying. So I'll talk about it towards the end. Just remind me. Okay, so let's begin with the class, guys, and let's start with nucleus. Okay, I wish everyone for their NEET preparation, bacha. Sarvanan. Hello Arshita, nice to see you all. All right. Good evening, Maha. Hello Nadeshwar, welcome. Hello Dexters. Hello Rishita. Hello Nadeshwar. Hello Naveen. Hello Kavya. HoD Physics means I'm the head of the Department of Physics. Okay. So let's begin, guys. Now we all know that everything around us is made of atoms, particles, right? Particles, the tiniest particles are atoms. The atom is further made up of smaller particles, namely 3 important things. One is the electron, which revolves. We have seen that in atomic structure in detail, right? Then the second part is nucleus. You know, and I hope you remember from the Rutherford's experiment, what did he say? The entire mass of the atom is not with the electron. It's with the nucleus. It's with the nucleus, correct? Okay. Now this nucleus is small, it's positive, and it is highly concentrated mass. Most of the atom is empty. If you think of the room as the atom, the nucleus will be a small dot in that room. It's that small, and the electrons will be going from the corners of your room. That nucleus gets that charge and the mass because of 2 smaller particles inside the nucleus. This is a rough picture of nucleus. Obviously, you cannot take a photo no matter what you do. It's just visualization. This is like out of creativity. This is how a nucleus looks like. It's made of tiny particles. One is proton, one is neutron. Why they got those names? Probably you'll get the idea from the first alphabet. P, proton, positive. N, neutral, neutron. Neutral, meaning it has no charge. Proton, P, positive. It is positively charged. So this has no charge, this has charge. Both of them, you can say that almost identical except for the charge factor and a small difference in mass. Otherwise, their masses are also very close to each other. All right. I hope this is clear. Very good, guys. Please tell important chapters. Okay, I'll make a video on that, Naveen, on this Saturday. Okay, just give me some time. It will take me some time to make it because I have to ask my team to, get all those chapters, do the analysis of the previous papers and give the highest weightage chapters for all the 3 subjects. Okay, I will do that. Now, if you talk about more properties of proton and neutron, like which is inside the nucleus, Look at these positive spheres. They are protons. The green ones are the neutrons. They do not have any charge. The symbol for a proton, and neutron, guys. For neutron, the symbol is N. Neutron, N. Proton, P, obviously. And like one would expect, neutron is a neutral particle, no charge at all. But there is a mass associated with it. The mass of a neutron, don't have to remember the value, this is just to give an idea. Just remember the first 3-4 digits, that's okay. 1.674, 10 to the power minus 27 kg. That's so small, guys. Your mass will be 50-60 kgs. Okay, probably if you take out a nail or something, it is going to be in few grams. This is 10 to the power minus 27 kg. That's the mass of the neutron. Okay, if you talk about the proton has a plus E charge. What does that E stand for? What is the value of E, guys? Come on, put it up in the chat box, spam it immediately. Plus E, what is the value? It is plus 1.6. Plus 1.6 into 10 to the power minus 19 coulomb. Exactly. Good evening, Zubair. Okay. Bharni, I'll be doing all the important chapters before your board examination from the board perspective and few chapters of 11th. And after your board examinations, the remaining things will be done. Okay. That's how it's going to go, bacha. You cannot expect everything to be done in just 1 or 2 weeks, because then it will be just hurried up, and I don't want to hurry up, and we have time till May. Don't worry about it. And if you're a dropper, you have even more time because you don't have boards. Mass is almost the same. There is a change only in the third decimal. This is 674, this is 672. The mass of neutron is slightly larger, very slightly larger than the mass of the proton, but otherwise they are roughly the same. You can see that over here. Everyone with me? Very good. Excellent. Thank you, Zubair. Love you too, bachalo. Okay, great. Next point that you should know about a nucleus is the different terms used with defining an element, like hydrogen, different from helium, different from sulfur, different from oxygen. How do you represent a sulfur atom or the sulfur element? There are three main things. One is the symbol, one is the atomic mass number, the second and the third one is the atomic number. Atomic mass, atomic number, and basically the element. So we will see that, but before that there is one more important thing, and that is the atomic mass unit, which is the unit of measuring the mass. Like you can see over here, guys, these masses are so small. Dealing with it is a problem. Imagine writing this 10 to the power minus 27, you will be like, to hell with these calculations, I don't care. So there is a smaller unit, and that unit is basically AMU, atomic mass unit, AMU. What is that? 1 AMU is 1/12 the mass of a carbon atom. Carbon atom's mass is very small. So 1/12, why 1/12? Because carbon atom has 12 particles inside the nucleus. 6 protons, 6 neutrons, so 12 particles. So 1/12, that you take it as a standard. And then you measure everything in terms of AMU. The value of 1 AMU is 1.66 10 to the power minus 27 kg. Guys, quickly tell me, is this mass very close to the mass of proton and neutron? Yes or no? Yes, definitely, Swayam. It will be helping you with the boards, but in boards you need to do some more things apart from just going over here, because boards is more of a theory. It's like a memory based exam, writing the answers neatly. NEET is more of thinking, your analytical skills, how you are spontaneously able to recollect some data points or use and apply the concepts. That's what NEET is. So approximately same? Great. So basically one can say that the mass of proton, mass of neutron is roughly the same, and it's very close to this value, 1.66. You can see that right from here also. Look at this, 1.67, 1.67. Okay, very close, and this value is also almost the same. So it's 1 atomic mass unit. Very good. Excellent. Okay. Now, Hari, please concentrate, bacha, on the lecture. Okay. This is not the JEE channel. This is a NEET channel. Okay. Now, the next important thing that you should know, like I was telling, is the representation. There were three things: atomic mass number, atomic number, and the element name. So guys, the first thing is X, which is the symbol of the atom. If it's helium, I will use He. If it's sulfur, I'll use S. If it is oxygen, I'll use O. So looking at that symbol only, you get an idea. Oh, this is oxygen. Okay, this is hydrogen. This is helium. Like that. Then you have Z. Z is in that nucleus, how many ever protons are there? If you count them, that decides the chemical characteristic of the nucleus. That is the atomic number, which is just the number of protons. That's Z. Last one being atomic mass number. Atomic mass number is the total number of particles inside the nucleus, which I call it as nucleons. So when I say the word nucleons, this nucleons means all those things which are inside the nucleus, basically protons and neutrons. So this value, atomic mass number, capital A, is the number of protons, which is Z, plus the number of neutrons. This is also a very important formula. And the way you generally represent any given element is something like this. Look at this. X is that element, like oxygen, atomic mass number on the top and atomic number below. So just to give you an example over here, it is nothing but like if I have helium and I say 4 over here and 2 over here, that means this 4 is the atomic mass number, this 2 is the atomic number. So there are 2 protons and 2 neutrons. Together there are 4 nucleons. So together there are 4 nuclear particles, that means nucleons. Is that clear, my dear students? Very good. Is that clear? Excellent. Awesome. Assignment questions. Niranjan, I have already shared the assignment questions on the Telegram channel. Whatever last session I did, na bacha, I already uploaded it on the Telegram channel, the NEET English Elite channel. So please have a look at it. When we do problem solving sessions, those problems with solutions as well as the homework questions and their answers are also uploaded. Great. Next thing that we can talk about is the 3 different relationships between all these elements. What are these 3 important relationships? Understand that, okay? Like you have brothers, you have uncles, you have friends. So elements also have some relationships. First relationship that you want to learn is isotope. Now in this relationship, they basically are very similar in characteristics, but they have different masses. Maybe like a twin brother or triplets, you might have heard of them. So all the 3 are very similar. They all like sweets, they all like to watch cricket, okay, or whatever. But one is very thin, one is really fat, another one is really fat. So that is basically called as an isotope. Hydrogen. Why is it called hydrogen? Because there is 1 proton inside the nucleus. Atomic number is 1, but mass number is different because here there is no neutron, here there is 1 neutron, here there are 2 neutrons, because out of the 3, 1 is the proton, remaining is the neutrons. I hope you get that. Same way over here. Oxygen, very similar. But what is different is the neutrons. So the mass number is different. That is called as an isotope. The next relationship is isobar. In isobar, their weights are same. Like your uncle might have the same weight as your cousin, might have the same weight as your friend. All are nice 60 kilos. Everybody is 60, 70 kilos. But one is your uncle, one is your friend, one is your cousin. They all are different. One likes cricket, one likes football. This guy likes sweets, this guy likes spicy food. So different in characteristic. So that is called as isobars. Look at that. This is hydrogen, this is helium. Completely different. This has 1 proton, this has 2 protons. But what is same is the number of nuclear particles. Nucleons. 3 nucleons. Proton plus neutron, the combination is the same. Total number. I hope that's clear. And same thing. This is carbon. Very different than nitrogen. Protons are different. But total nucleons, that is atomic mass number, is the same. You can see that right over here. Okay. Last one is isotone. When I say the word tone, N is being stretched now. When you say isotone, N stands for neutron. So in isotones, what is same? Neutrons. The number of neutrons is same. Look at these elements. 3Li7, 4Be8. Doesn't look similar, but what is same is the neutrons. 7 minus 3 is 4. 8 minus 4 is also 4. There you go, 4 number of neutrons. Same number of neutrons, isotones. This and this. 3 minus 1, 2. 4 minus 2, also 2. So 2 neutrons, so they are isotrons. That's all. So isotopes, same atomic number. Isobars, same atomic mass number, that's the top. And isotones, same number of neutrons. That's what it is. Great. So what we are doing is, right now we are studying nucleus. What are the different parts of the nucleus? How do you show the nucleus? What is atomic number? What is mass number? What is neutron number? What is the relationship? That's what we are learning. One of the last things in this is the radius or the size or the density of the nucleus. Now, if there are more particles inside the nucleus, it will become big. Like, for example, if I take helium, it barely has 2 protons, 2 neutrons. So 4 particles are there. But if I take oxygen or carbon, carbon has 12 particles inside. So big. So obviously the size grows as you add more protons and more neutrons. That means what matters is the atomic mass number. Atomic mass number is what matters in deciding the size of the nucleus. And the size I can calculate by measuring the radius of the nucleus. Nucleus, if I take it like a sphere, the radius of the nucleus is dependent on the atomic mass number given by this relationship. What is the radius of the nucleus? It is A raised to 1 by 3. A is nothing but atomic mass number, R is nothing but the radius. So you can think as if this is the nucleus, this is the radius. There will be also some volume which will be 4 by 3 pi r cube. This constant of proportionality comes out to be R naught. This R naught has a rough value of 1.2 FM. If you are wondering what is this FM, sir, I have heard of radio FM. What is this FM? Here this F stands for 10 to the power minus 15. So it's so small. 10 to the power minus 15 Fermi. That's the level. You know, milli is 10 to the power minus 3. Micro is 10 to the power minus 6. Nano is 10 to the power minus 9. Pico is 10 to the power minus 12. Fermi is 10 to the power minus 15. That's very small, guys. This is the radius that you get. Now you can also calculate the density of the nucleus, how dense it is. So that density will be the total mass of that nucleus upon the volume of the nucleus. Okay. Now one thing I can see from here in calculation of volume, this will be 4 by 3 pi r cube will make it r naught cube into a raised to 1 by 3's cube. A raised to 1 by 3 raised to 3 will become a. So this just becomes 4 by 3 pi r naught cube into a, correct? So why not use that over here? So downstairs I'm just going to use 4 by 3 pi r naught cube into a. What's going to come on the top? What's going to come on the top? Total mass of the nucleus. Nucleus has particles. How many particles? Protons and neutrons. Just count them. Let's say 12, let's say 10. What is the 10, 12, 100, whatever? That is the atomic mass number. So that means the number of particles into mass of each particle. So mass of each nucleon into atomic mass number will give me the total mass of the nucleus, correct? What happens? AA cancels, guys. AA cancels. So I'm just left with mass of the nucleon. This 3 goes on the top. The whole thing divided by 4 pi r naught cube. That means if this is just a number, it's going to be like, some value. 3 is a value, 4 is a value, pi is a value, r naught is a constant. So this is also going to be a constant. That means it is independent. It is just independent of the atom. Completely independent. Iron might be this big, sulfur might be this small, helium might be this small, but all of them have the same density. This is the proof for that. Yes, density of all the nucleus is constant. Hello Manaswini Banela, welcome Bachalo. Good evening. Hello Danish, nice to see you guys out here. keep attending the classes. Make sure smash the like button and also hit the subscribe button. Very important, guys. I don't want you to miss any of the classes. Okay, very simple and important things about the nucleus. Moving on, oh, by the way, I have kept the printed material as well. So I hope you know you are going to get all my material on the Telegram channel. You will get the printed as well as my handwritten notes. Great. So let's see. What do you think is the relationship between these two and these two? Isotopes, isobars, isotones. What do you think? I want everybody spamming in the chat box, guys, right now. Come on, let's see how many of you are going to spam and get the right answer. Let's get you guys on the screen also. There it is. Okay. Come on, come on, come on. Figure this out. What do you think is the correct answer to this particular question? Option B says Salva Kumari. All right. What about others? Others, come on. Let's see how many of you are going to be correct about this. How many of you are going to be correct about this? Come on, guys. Figure this out. What is the correct answer? A, B, C or D? A, B, C or D? Yes, the correct answer is B, and our lovely warriors have won this. Very good. You can see over here 76, 76. So obviously atomic mass number is same because A is same. Here 30 minus 14 is 16. 32 minus 16 is also 16. So they are basically isotones. Basically N is same, which is A minus Z. That's it. Option B. Very nice. Perfecto. Now, let's talk about the next concept. We have talked about what a nucleus looks like, what is it made up of, how do you show it, how a nucleus is formed. Is it stable or is it unstable? Is there some energy involved? Is there some force involved? Let's talk about that before going to radioactive nucleus and all that, or nuclear reaction. Now, if there are two positive charges, yes, Pandu is here. A lot of you were requesting, sir, where is Pandu, sir? So there we have our amazing Pandu. And this Pandu starts wondering, proton do not like each other. It happens, right? In your school, you don't like somebody. Sir, I don't like sir. He always teases me. He bullies me. Or he's always rude. Or he's random. He's mad, psycho. And that person is also like, I also don't like you. You are doing this, you are doing that, you don't care, whatever. There is always a mutual repulsion, okay, between maybe some two people in the school or maybe in your society. Same way, two protons also don't like each other. What is the reason for that? Electric force. But proton and electron like each other. The moment proton sees the electron, it will be like, come to me. But electron will be like, listen, I can't fall into you. Then there will be a big explosion. I will revolve around you. So the electron revolves around the protons or the nucleus using the electric force of attraction, right? Just like the earth revolves around the sun, because of mutual force of gravitation, right? But proton, they don't like each other. They're like, go away, go away. How do they stay together? What's the reason for that? So in general, you can say that there must be something much stronger, something more superior than the electric hatred force or the repulsion force which brings them together. Like if there are two enemies and then, you know, teacher is like, you Pandu, come sit here. Oh, you Laddu, come sit here. Sit on the same bench as Pandu. Pandu and Laddu don't like each other. They hate, they repel. But teacher made them sit together, do the same assignment or project together. They don't like, but still they are together. For some reason, what is that force? Teacher force. Teacher force made Pandu and Laddu sit together. They were actually enemies. They don't like each other. So if two protons are staying together, there must be something superior than electric force or gravitational force. That is basically your nuclear force because it is inside the nucleus. And this nuclear force is the one which holds the protons and protons, neutrons and neutrons, or neutron and neutron, proton and neutron, proton and proton together. Teacher forces, correct? Just like you guys are staying over here on this channel because of teacher force, right? Correct. Maybe there is some person you don't like. Hope not. Hopefully all of you are friends, right? Correct? Great. Now, what is this force? What does it depend on? Gravitational force, what does it depend on? Mass m1, m2 and distance. Okay. Electric force, what does it depend on? Charge q1, q2 and distance. Nuclear force, is there a formula? Well, there is, but you don't have to study it. Like, sir, thank God, one link less in our NEET syllabus. You just need to know the basic traits of a nuclear force. So, nuclear force depends on something else only, and it is basically the spin. It depends on the spin. It depends on the distance, but not so much. It's like, you know, two particles are there, there is a nuclear force. You increase the distance between them, the nuclear force hardly changes, and if you increase the distance further, tuck, it drops. Suddenly it goes down. So it is there only in a certain region, and it is very small range for which the nuclear force acts. As soon as you increase the distance, immediately it drops down. So it's a very saturated force. It's a short range force, but it is very strong, very superior, stronger than gravity, stronger than electrostatic. And it does not depend on the mass or the charge. It depends on the spin. Very good. Manasuni, where is Champa? In love stories, today we are learning hate stories, so that's why Pandu and Laddu came. When we learn some love story, then I'll bring Champa and Pandu also. Don't worry about it. Okay. So I put up all the properties that I just explained to you in the points form. You will be using these points in your boards, or maybe they might just give you as an objective question. Which of the following is not a characteristic of nuclear force? So it is basically independent of the charge. It does not depend. It's a very short range force. It's saturated. It is not going to follow that formula Q1 Q2 by R square. So it's not a central force. Central force means it should follow that formula, Q1 Q2 by R square or M1 M2 by R square, that kind. It's not. Okay. So these are the main characteristics of the nuclear force which you should know. It's a fundamental force. I understand that. Just like you have gravity, you have electromagnetic, there is nuclear. Then nuclear also, there are two more forces like short nuclear and strong nuclear, or weak and strong, but you don't have to go so much into detail as of now. Okay. Now what is the meaning of exchange force? Very good, GV. So like when you have two masses, there is a force. Just because those two masses are there, there is a gravitational force. In nuclear forces, what happens is there are particles which go from here to here, and there is one particle which goes from here to here and is like, hey, listen, I am there with you. It's like sending a messenger. Okay, we both have to attract each other. Okay. Then this guy also passes one chit, like it happens in school, na? You pass one chit, like, hey, listen, let's do this, let's do that. Listen, after the break, let's go here. So that is a chit. So they send messages like you send WhatsApp, na? Like that. Okay. I hope this is clear. Everybody with me? Let's now go to the ultimate question. Okay. Now, this is going to talk more about the stability. Let's more talk about the stability of the nucleus. Let's talk about even the, what is the mass defect and the energy associated with the nucleus. All these things are going to come from this particular slide. Now, what is mass defect? Everything we are going to talk, just understand what I'm asking and answer the question in the chat box. Imagine I take helium. Helium, what does helium have? Helium nucleus have? It has 2 protons and 2 neutrons. 2 protons and 2 neutrons, right? Okay. Karpana champ, you don't have to take notes in my class because all these slides will be available. Number 1. Number 2, you can make running notes only for the formulas or important things. It will be there in the slides, but just so that it enters your head. Don't have to make long notes. If you already have your notes, then just add the extra points that you learn. That's all. 2 protons, 2 neutrons. Okay, that's a helium nucleus. On the other side of the beam balance, I have 2 protons and 2 neutrons. Which one will be heavier? What do you think? The helium nucleus, or the 2 protons and the 2 neutrons? Answer it in the chat box, guys. I'm waiting to hear your answers. Salva Kumari says the mass of the nucleus is less, so that means this will go up. These 2 protons and neutrons separately where you have placed it, this will go down. That's what she says. Emily says more, equal, same, equal. Interesting answers out there. Come on, let's see how many of you can get this. Is it going to be, which one will weigh more? Helium nucleus, protons and neutrons, or both will have the same weight? A lot of you are going to get it wrong. A lot of you are going to get it correct. So the ones who are correct are the ones who are saying option C. Yes, GV. Yes, I think you are the first one to tell it. Yes, you will be like, what nonsense. Let's bring Pandu and Champa. Somebody was saying, sir, where is Champa, sir? I'll bring Champa now. Pandu weighs 60 kilos. What is the weight of Pandu? 60 kilos. Pandu. There is Champa, his girlfriend. Champa, her weight is 40 kilos. Pandu, 60 kilos. Champa, 40 kilos. Pandu, 60. Champa, 40. What is their total weight? Answer in the chat box. Pandu, 60. Champa, 40. What's their total mass? What's their total weight? Come on, guys. Answer in the chat box. No, electrons will not contribute in the mass. We are ignoring that. 100. Very good. Now, Pandu met Champa. He became very happy. He's holding her hand and walking in the park, or just putting his arm around, and they both are walking nicely. They're dreaming. They're talking about something. This is imaginary Champa, guys. Okay. So imagine this is imaginary Champa. This is imaginary Champa. Okay. And now I ask you, what is their total mass? You're like, sir, 100. Sir, Pandu's mass is 60. Champa's mass is 40. Total mass is 100. Then you ask them to stand on the weighing machine. You ask them to stand on the weighing machine. They stand together. They find that their mass is not 100. Their mass is 95 kilos. They'll be like, what just happened? Then they're like, okay, wait, let me do this again. So Pandu goes and stands separately. He sees 60 kilos. Pandu steps aside. Champa comes. 40 kilos. Lights. Okay, 60 plus 40, 100. Now, both of them come, stand together. They both are standing together. Their weight, 95 kilos. They're like, what just happened? Where did that 5 kilo go? Mass defect. Something is defective. Mass defect. It is basically the mass defect. You're like, sir, how this mass defect? Where is that mass going? Somebody ate, huh? Sir, Laddu came and ate Pandu. That's why, sir, 5 kilos less. No, Laddu did not eat Pandu. You will eat Laddu, no? You eat Laddus. How can Laddu eat you? Okay? You cannot eat Laddu. Sorry, you can eat Laddu, Laddu can't eat you. So nobody has eaten Pandu or Champa, guys. So energy is the word. I am seeing the word energy. Very nice. This was the theory which Einstein proposed. I am going to come to that. But for now, what is mass defect? It is found the mass of the nucleus is always less than the sum of the masses of its individual particles freely. So protons and neutrons, if you weigh, it's always more. Nucleus is always weighing less. This difference is called as the mass defect. This is called as the mass defect. So basically, the mass defect is the mass what you are expecting minus the mass which is actual, like it happens in reality also, right? Sir, I am expecting 170 marks in physics. Actually, sir, I got 150 marks only. So 20 marks is the mass defect. Mass defect is what you are expecting. You are expecting 100 kilos, but you got 95 kilos. So 5 kilos is the mass defect. Agree, disagree? Agree, disagree? Got it? So this is mass defect. Excellent, guys. Expected minus the actual. Usually, you will see it in many books that it is basically the mass of the, what do you say? You are expecting it to be mass of protons plus mass of neutrons minus the mass of the nucleus. That is how it is usually calculated also. Okay, mass of protons plus neutrons minus the mass of nucleus, which is actual. This is expecting. Total mass. By the way, this is the total mass. Okay, great. Now, like I was telling, that this mass goes somewhere. Where does it go? It goes into energy. That's what Einstein said. That's what Einstein said. See, Einstein said, when you destroy mass, you break that mass, top, gone, poof, something else is created. What is created? Energy. Energy is created. Mass is destroyed, energy is created. Somebody destroys energy, mass is created. both are interchangeable, convertible. There is equivalent mass for some energy. There is equivalent energy for mass. Both are interchangeable. So what is the relationship between them is given by Einstein's famous equation, which is very simple. And most of you already have put it up in the chat box. Proud of all of you guys that energy which is created or destroyed is related to the mass which is destroyed or created into c square. This is the formula. But what happens is, if you put 1 kg mass also, just imagine you take 1 kg and destroy 1 kg mass. Look at the energy which will be created. C, what is the value of C? 3 into 10 to the power 8. C is 3 into 10 to the power 8. So guys, if I take delta M is equal to 1 kg, C is 3 into 10 to the power 8, I will get energy as 1 into 3 into 10 to the power 8 square, which will be 9 into 10 to the power 16 joules. This is crazy, guys. Look at that energy. It's not 5, 10, 100 joules, 1 lakh joules. No, it is 10 to the power 16 joules. It's in trillions and millions of joules. So much energy will be created by just destroying 1 kilo of mass. It will solve all our energy problems. Now, this energy is very huge, but usually the masses which we talk about are also very small. It's not in 1 kilos. 10 to the power minus 27, minus 28, that's small. So the masses are that small, the energy is not this big, it is also very small. So what do? Convert mass into atomic mass unit. Remember the small unit of mass. C value you put and convert the joules into electron volt. Convert the joules into electron volt. Yes, for nuclear reactors and all that, this is the scale of the energy. Yes, Emily. So when you convert it, it looks like this. Delta M in atomic mass unit multiplied by the conversion factor is 931 mega electron volt. This is the formula which you will be using more frequently, but keep in mind this mass defect is in AMU, not in kgs. This was in kgs. This was in SI units. This is not SI, this is AMU converted into electron volt, not joules or SI unit. Very good. So when you destroy 1/12 the mass of carbon atom, which is 1 AMU, you get 931 mega electron volt. That's why nuclear reaction is very powerful and very energetic. You have to burn so much of coal to get that much energy. You have to lay so many solar panels to get that much energy. To destroy few atoms here and there, that's it. So much of energy will come. That's why nuclear energy is very powerful, and unlike what people believe, where nuclear reactions are very scary, sir, very dangerous. Actually, nuclear reaction or nuclear energy is much cleaner and much more safer than the other forms of energy. In fact, it's said that a lot of animals, like especially birds, die because of windmills. Because of the wind turbines, a lot of birds actually die. And also solar energy is so costly to make because of the silicon requirements and all of that, because of the semiconductors. So actually speaking, nuclear, although it looks dangerous, causes much fewer deaths than coal related deaths, or the cost which is involved in other energy setups. It's crazy. Now let's talk about something called as the binding energy. Why is it not the major energy supply? Because people get scared. It's because people start protesting. Oh, I don't want nuclear power plant. It will cause explosion. Yes, nuclear explosions are dangerous. If you get exposed to nuclear reactions, then your skin will burn. You might die. But that is so rare. It's so rare that you might probably die breathing the air which is produced from the coal plants because of that carbon dioxide and carbon monoxide. That's how it is. But we cannot see that. You don't feel it because it happens over a period of 10, 12 years or 20 years, right? But nuclear reaction related death will happen instantly. So people are scared, but it rarely happens if you see the data. That's how it is. Okay. Yeah, people are reminded of Hiroshima, right? Okay. So talking about binding energy. What is this binding energy? See, when I take these protons and neutrons and I put them together, the mass of the nucleus is less. So let me just put it over here. That energy which is created is called as the binding energy. Let me explain this to you. I have certain protons and certain neutrons separately. They combine together to form a nucleus, maybe helium. Example, this is your individual protons. These are free protons and neutrons. This is your nucleus. I know that the mass of the nucleus is lower than the mass of the free protons and neutrons. So there is a mass defect. So as you can see in this transition, if this guy's mass, the total mass is m1, this guy's mass is m2, m2 is obviously less than m1, hence there is definitely a mass defect, which is m1 minus m2. m1 is higher than m2, so there is a mass defect. So the mass has been destroyed. So here mass is, this delta M mass is destroyed. If the mass is destroyed by the principle of equivalence, something should be created. If the mass gets destroyed, the mass becomes smaller. What is created? Energy is created. So mass is destroyed. So energy is basically created. This energy which is created is called as the binding energy. What is it called? The energy released in the process of creating that nucleus is called binding energy. Why binding? Because you're binding, you're putting them together, binding them, putting them together. That's why binding energy. So mesons are basically those nuclear force related particles. You don't have to go there. Those are those exchange particles in nuclear forces. If you do PhD and all that, then you will learn more about it. Okay. Obviously, Harshu, it's not that real name. It's obviously students who call me out of love, and that's why obviously I love students. I love teaching. So because if students are calling me, so that's why I put it in my name itself. In all my Instagram handle, Twitter handle, everywhere you will see the word captain. Okay. Now this binding energy is calculated by, this binding energy is just calculated by delta M into C square, where the delta M is the total mass of the proton plus the neutron minus the mass of the nucleus. This is how you calculate it, or you can also use 931 into delta M mega electron volt, whichever you want to use, this or this formula. Okay, great. Yes, minions have given me the name. Very true. Excellent. Now let's talk about something else, and that is basically binding energy per nucleon. Like, sir, what is this binding energy per nucleon? I'll give you a simple example, then you will get an idea. Imagine, let's bring in Pandu. Let's bring in Pandu, guys. Pandu donates some money to poor people. How much money he donates? 1000 rupees. 1000 rupees. To how many people? To, let's say, 10 people. 10 people, he donates 1000 rupees. So each person, one person will get how much rupees? How many rupees? 1000 divided by 10. That's going to be 100 rupees per person, per poor person that he donated. Very nice. Camera is not focusing well, I'm not sure, bacha. It should be. I've just adjusted it. I'll just adjust it again. Oh, I understood what was wrong. It was on autofocus. So when I move back and forth, it was changing the focus. So that was the problem. Thank you for reminding me. Okay. Now let's take Champa. Champa is also donating. So Champa decides, if Pandu donates 1000 rupees, I will donate 10,000 rupees. So Champa donates 10,000 rupees. But she donates it to more people. 1000 people she gives it. So each person will get how many rupees? Each person will get how many rupees? Yes, autofocus is now off. Usually I keep it off, but today I think I forgot it. Now, yes, GB, correct. She will give 10 rupees per poor person. So 10 rupees. Now, if you are a poor person, would you like the donation from Pandu or Champa? Put it up, spam it in the chat box. If you are a poor person and you want some donation, where would you want to be? Would you want to take the donation from Pandu, or would you want to take the donation from Champa? Selva Kumari says Pandu, GB says Pandu, Somika also says Pandu, Prem, Karpa, Sampath, Hamshi also says Pandu, Lenasis also says Pandu, Varsha, Vijay, Roshni, Murshida, very good, everybody says Pandu, excellent. Although Champa gave a lot of money to many people, what matters is per person how much money did you give. So that brings us to the concept of binding energy per nucleon. Now I'll give you why this concept is even more important. Now see guys, this binding energy is the energy released. Now when more energy is released, where more energy is released, it becomes more stable. Just like, sir, I was very frustrated, very tensed. I was very angry. I don't know, I had mixed feelings. Very irritated I was. So you know what I did? I shouted at so many people. I did so many things. I was playing games. I released my frustration. And then I calmed down. So you release your frustration, you release your anger, and that's when you calm down. Same way, these atoms, these nuclei also, when they release the energy, they calm down. That means they become more stable. Everybody gets this? Everybody gets this? I know, Prem, you can argue with so many different factors like, sir, she gave more money to more people. I'm not going there, but this was just to explain you the concept of binding energy per nucleon. So now, when the binding energy is released, if you count it per nucleon, if more energy is released, that means it is more stable. If less energy is released, it is less stable. More energy is released per nuclear particle, it is more stable. If less energy is released per particle, it is less stable. That's what this binding energy per nucleon is. So you just take the binding energy and divide it by the nucleus, so number of nuclear particles. So binding energy per nucleon, this is the formula. This is nothing but delta M into 931 mega electron volt divided by atomic mass number. So if it is chlorine, you might most likely divide by 35. It's, hydrogen, it's just 1 or 2 depending on the isotope, and if it's helium, you might divide it with 4. So depending on the element, you are going to divide it by a suitable atomic mass number. So per nuclear particle, per proton or neutron, how much energy is given? It decides the stability of the nucleus. Now what scientists did, they took all the elements of the periodic table. Imagine how much time will be needed for this. All the elements you take, calculate the mass of the proton, calculate the mass of the nucleus, subtract the two, find the mass defect, multiply by 931, divide by A. For this is the binding energy per nucleon. Then take the next element. Again, calculate the mass defect, calculate the binding energy per nucleon. They did it for all the elements of the periodic table. So guys, you need to be really motivated, and really you need to have that, find a time to do all this. And they plotted a graph, and the graph came out to be like this. Look at this graph. For hydrogen, depending on the isotope, very close to 2 mega electron volt per nuclear particle. If you go to higher elements like nitrogen, carbon, oxygen, comes to somewhere between 6 to 8 mega electron volt per nuclear particle. It kept on increasing from sulfur to etc. to iron, and after iron, which is close to like 9 or something, 9 mega electron volt per nuclear particle, it starts dropping to higher elements. Somewhere around uranium, it goes down till as close as 7 mega electron volt or something like that per nuclear particle. From this graph, who do you think is the most happiest nuclear particle? Exactly, Prem has already answered it. For iron, it is maximum the nuclear energy which is released per nucleon. So guys, that is the most stable element. So these people will be jealous of iron. Yes or no? They'll be like, oh my god, look at him, so much energy he released. These people will also be envious or they will be jealous of iron. They also want to come down to iron because there is more energy per nuclear particle. So this graph also gives you the stability chart of the nucleus of any element. Okay, but don't think, sir, hydrogen is jealous of iron. No, why can't it become iron? Is it so simple? Is it so simple? Hydrogen says, hey, listen, come no, I have something secret. See, look at this chart, what I found. See, well, let's become iron. Let's become iron, will be more stable. That hydrogen will be like, get lost. I am hydrogen, I am going to stay hydrogen. Nobody, Papa, will listen to that hydrogen. They'll be like, tata, bye bye. Hey, I'm not going to listen. You need to literally force them. Hey, come man, sit here. Wait, I'll tell you, you will get more energy per nucleon. You have to bring all these people together. Hey, sit together, man. There is more energy released. You have to force them. And then they'll be like, what? Really? So much of energy per nuclear particle? And they will become iron. So you have to literally make in a lot of effort. And they'll be like, oh my God, I never knew this would happen. So these reactions take a lot of effort, lot of energy to bring them into that particular stable state. Sometimes it is natural. We'll come to that as well. Sometimes it is forced. Yep, very true. So Parnika, even now the focus is not clear? Really? I think it should be fine. Yes. So we are going to come to fusion and fission in a bit, but before that, let's talk about this question. Okay, what do we have? Two neutrons undergo nuclear fusion to form helium. Energy in the process is how much? Let's talk about it. Let's first write it down. Two deuterons. Deuterons means hydrogen, atomic number 1, atomic mass number 2. Two of them, so 2H1, 2 into 2H1 combines to give you what? Helium. So helium is He, atomic number 2, atomic mass number 4. It makes sense. 1 into 2, 2, 2 into 2, 4. It is a proper balanced reaction. Okay. Now, how do I find how much energy is released? How much energy is basically released? Simple logic. Observe all the steps. I'm going to explain you the details and then I'll give you a general formula. You will avoid all these steps. Okay? Observe. First, if you want to just form hydrogen, I will need one proton and one neutron which combine together to give you basically one hydrogen nucleus. One hydrogen nucleus, in fact, in the form of deuteron. This is the deuteron isotope, okay, of hydrogen. Now, since I want two hydrogens, okay, over here, so two protons plus two neutrons give me two deuteriums or two hydrogens over here. Okay. Now, energy per nucleon, observe this carefully. Per nucleon, for deuteron is 1.1. For deuteron is 1.1. Correct? In deuteron, how many nuclear particles are there? I will tell you, bacha. First, observe this. How many nuclear particles are there in deuteron? 2, right? One proton, one neutron. So, how much energy will be released? 2 into 1.1, right? 2 into 1.1 mega electron volt. Very good. When there are two deuterons, not one, two. So this will get multiplied by 2. So 2 into 1.1. This whole number, what is it value? 2 2s are 4. 4 into 1.1 is 4.4 mega electron volt. Keep this on the side. Keep this on the side. Don't do anything now. Very good. Now look at the other particle, which is helium. Helium can be formed by, again, take two protons, take two neutrons, and then it combines to give you one helium nucleus. In helium, per nucleon, the energy is 7. Now, how many particles are there in the helium nucleus? 4, right? 2 protons, 2 neutrons, so 4 particles. Per particle, 7. So for 4 particles, 4 into 7, which is nothing but 28 mega electron volt. Correct? Very nice. Now observe this. 2p 2n, 2p 2n, LHS is equal. If LHS is equal, what will be RHS? Equal. LHS is equal, RHS will be equal, correct? So let's use that. So 2H1 plus, how much was it? 4.4 will be equal to, what do I get over here? 4He2 plus, what is it? 28, correct? Let's just rearrange this. So I'm just going to keep this as it is over here, 2H1, okay, is equal to 4He2, correct? 28, oops, plus 28 minus 4.4. That is what I get on the right hand side. So what does this tell you? What does this tell you? This reaction is going like this forward. I should not put equal to, I'll put arrow marks to show that it is a reaction. I think this reaction is similar to this reaction. I think I just got the energy from this. So guys, what is the energy which is basically released? That energy is nothing but 28 minus 4.4, which is just nothing but how much? 23.6 mega electron volt. Exactly, guys. That's option D. Now you might be like, sir, this is a headache. So many things I have to do. Yeah, this is the logic. I have explained it to you in detail. But if you want to avoid that, there is one simple shortcut trick. So whenever you have to find the energy which is released, what you do is, look, what is 28? 28 is the binding energy. 28 is the binding energy of, what is this? Product or reactant? H, hydrogen is the reactant. Helium is the product. Helium is the product, correct? So what is 28? Is the binding energy, the total binding energy of helium, correct? So can I say it is binding energy of the product? And what is 4.4? 4.4 was the binding energy of hydrogen, which in this case is the reactant. It is reacting. So minus binding energy of the reactant. That's it. That's it. Exactly. Product minus reactant. Very simple formula. So you can avoid all this nonsense. If you want to avoid all this nonsense, you can just remember this formula. Easily you will get it. Isn't it amazing, guys? The difference of the binding energy is as simple as that. Now let's go to the next part. Very nice. Very nice, guys. The next part is basically the nuclear reactions and the particles that come out. You might have seen in movies, they carry some rods, uranium, thorium, etc. and they look as a shiny, bright, because there is some nuclear reaction happening. And these nuclear reactions are very dangerous. So they are often enclosed in lead boxes or very thick cement and lead, because they have properties of absorbing all the harmful radiations which come out of a nuclear reaction. Okay. So what are the kind of particles that come out? There are three major particles. One is called alpha, one is called beta, the third one is called gamma. So what is alpha particle? Alpha is basically doubly ionized helium. So usually the symbol for that is nothing but alpha, atomic mass number 4, atomic number 2. Mass number is 4, number is 2. The second one is beta particle. Beta particle is nothing but, simply put, an electron. The symbol for a beta particle, because it's an electron, mass number negligible, so put 0, but atomic number -1, because if it is there in the nucleus, imagine if an electron enters the nucleus, it will cause a negative effect. That means it will not add to the charge, it will reduce the charge, because it's negatively charged particle. So that's why -1. Okay. Last one is gamma. Gamma is nothing but the photon, not proton, photon, which is basically light. Gamma has no mass number nor any atomic number, 0, 0. Exactly. Very good. Okay. Now, if I apply electric field or magnetic field, which of these will get affected by it? Put it up in the chat box. Which of these will get affected? Put it up in the chat box, guys. Come on. This is what chapter, sir, I'm studying. Very good, Sanjay. Oh, you have modern physics in 11th grade only. Which board are you in, bacha? Alpha will get affected, beta will get affected, but gamma, no effect. Gamma unaffected. Very good, Salva Kumari. Gamma is not affected, but gamma is the smallest. Alpha is the largest. Alpha is the heaviest. Beta is medium, and beta is actually fast. Gamma is the fastest. If you compare the speeds, alpha bulky, right? Big boy. Aram se it will go. Aram se. Heavy mass. Beta very small. Zoop, it will go. Gamma is light. Light will go the fastest. Nothing can beat the speed of light, guys. Fastest. Okay? But because it is so fast and it is so small, it can also penetrate a lot. Alpha, not so much. Beta, a little better you can say than alpha. Okay, guys? Alpha is the least penetrating. Beta is slightly more. Gamma is the highest and the fastest also. Awesome. Awesome. There are simple things that they do when there is a nuclear reaction. When there is a nuclear reaction. Okay. So I have put up all the three things over here. Observe carefully. If there is alpha decay, meaning a nucleus emits alpha particle, you will notice, because an alpha particle comes out, the atomic number, because alpha particle means 2 protons, right? So atomic number will reduce by 2 and atomic mass number will reduce by 4. You can see this is basically the parent. This is called as the parent, and this one is called as the daughter, the child nucleus, daughter nucleus. That's what it is called. That's what an alpha reaction does. Everybody clear? So 2 protons and 2 neutrons separate out, they become alpha particle and they're shooed away from the nucleus. Great. That's what an alpha reaction does. When you talk about beta, what is it doing is inside the nucleus, there is one neutron. It splits into a proton and an electron. Proton and an electron. So think what is happening. A neutron is there, neutral particle. Suddenly it becomes a proton and an electron is just thrown out. So the moment it becomes a proton, what will happen? Charge will increase. So the atomic size will not change, but number will change because protons is 1 excess. So that's why you can see atomic number increases by 1. There is no change in the atomic mass number because neutron became a proton, roughly the same mass. The electron is just thrown out, which is called as the beta particle. Very nice. Now in gamma, you'll be surprised to see atomic mass number same, atomic number same, it's balanced 0 0. A plus 0 is A, Z plus 0 is Z. Like what is this, sir? Nothing has changed. Actually something has changed, and that is at nuclear scale. So actually what happens is, this is an excited nucleus. Do you remember atomic structure? Different states of hydrogen like atoms in Bohr's model. Electron is in excited state, goes to ground state. What does it emit? Electron, when it goes from excited to ground state, remember Lyman-Balmer-Paschen series? What will happen? It will release light, photon. Same way, a nucleus, not the electron, nucleus can be excited, very happy. It becomes unhappy, okay, done. It releases what? Light. So this is basically your ground state. This is basically your ground state. So that's why you are getting a photon. Yes, electromagnetic waves. So Emily, usually the duration of the lectures is anywhere between 1 hour to 2 hours. Anywhere between that, depending on the chapter, depending on the many factors, what is there in that particular subtopic and all of that. Okay, there is no fixed rule. Okay, great. There are more properties. I have put it up in the chart form. This is particularly useful for your board examination. Please go through these charts and these data points after the lecture is over. Okay, but otherwise you have got an idea of what an alpha, beta, gamma reaction is and what these particles are, along with their penetrating powers and their deflections from electric fields. Correct? Okay. Now let's talk about 2 things. One is fusion and is fission. Fuse, bring together. Fission, cut, break it. So fusion and fission reactions. So when 2 or more elements, they feel that okay, we can be together and then I can become a more stable nucleus. That's a fusion reaction. But if there is a nucleus it likes to be separate and make smaller nucleus to become more stable. That's a fission reaction. So a good example of fusion reaction, here it is. Observe, there is one tritium, that's the isotope of hydrogen. This is a deuterium, hydrogen's isotope. They fuse and they combine to form helium, and one neutron is left out. Conservation of the number of particles, 3 particles plus 2, totally 5 particles, fuse, okay, 4 over here, 1 here, again 5 particles. That's it. So this is a fusion reaction. They are brought together with lot of pressure and at a very high temperature together. That's what happens. There are many examples. This is just one such example what a fusion reaction is. In fission, look at this. This is such a bulky element. A neutron goes and hits it like you strike a coin in a carom board, and that's it. It breaks apart. Happens, right? Even in a pool or snooker table, all right? You hit it, all those balls get separated out. So same with this, neutron is bombarded onto that heavy nucleus. It splits into smaller daughter nuclei. Okay. Oh, is it Prem Kumar? I don't know. Maybe you should tag me or send me. Maybe give the translation also. Yes, fusion occurs in the sun, fission occurs in nuclear plant. Oh, by the way, remember, now fusion reaction is possible at a very small level. I'm pretty sure if you have seen Iron Man, he has this fusion reactor right at his chest, right? So fusion is the next level technology. When we use nuclear power plants, right, in that there is fission happening. So there is uranium is disintegrating, and then it gives you smaller elements and releases energy. So that is fission reaction. Till now, we have not been able to use fusion so well. It happens in the sun, but the day that happens, our level of energy will be next level. Right now, we are dependent on petrol. Now, slowly people are like, okay, we should use wind energy or we should use solar energy, and we can use electric vehicles, not polluting and all of that. But electric vehicles, no, it's not the future. It's the fusion vehicles which are going to be the future, where you will have fusion technology, fusion reaction happening inside your car, inside your house. Just imagine there is a nuclear tiny reactor, just like Iron Man has it on his chest. You have such a reactor and it is creating energy. You don't need to fill it, you don't need to charge. Who is going to put that plug over there and charge it? Not required. You have a fusion reaction. So that's the new technology, and it was just done successfully by a lot of scientists, and I think that's going to be the future. No need of petrol, no need of anything else, no need of solar, guys. It's going to be crazy. Now, in any fusion or fission reaction, there is some energy involved, like the one over here. Look over here. Where did that problem go? This problem. This was a fusion reaction. Did you see that? 2 hydrogens meet to form helium. Energy is released. That's a fusion reaction. So you got some energy released. This energy which is released is called, or absorbed, depends what is happening, it's called as the Q value of the reaction. Q value of the reaction. So guys, this is called as the Q value of the reaction, which is binding energy of product minus binding energy of the reactant. So I'm just going to put it over here. So the Q value of the reaction is basically that energy which can be either released or taken in, that is binding energy of the product side minus binding energy of the reactant side. That is what the Q value of a reaction is. If the Q value is positive, that means it releases energy. It releases energy. If it is negative, it means it takes in that energy. That's all. Okay? I hope this is clear. Very nice. Excellent. Let's do some questions based on this. In the given reaction, from this to this, this to this, this to this, which are the particles which are emitted? Alpha, beta or gamma? Come on, figure this out. Come on guys, figure this out. What's the answer? Video is blur. Why is that happening? I hope it is fine now, bacha. Also check your settings of YouTube. Option B for sure. Let's have a look whether you guys are correct. Yes, you guys are correct. Perfect, guys. I think you can see that over here. Atomic number is increasing. Obviously, it is beta reaction. Atomic number increasing. There is no change in atomic mass number. Here, atomic mass and atomic number are decreasing, so it's emission of alpha. Here, there is no change, so it is gamma. So beta, alpha, gamma. Beta, alpha, gamma. Perfecto. Perfecto. Very good. Proud of all of you guys. I think there was nobody who answered it wrong. I think there is. Oh, the moment I said somebody answered it wrong. Yeah, guys, it is option B. Let's see if you can solve this. Binding energy of A and B are EA and EB. What is the Q value of reaction if 3 atoms of B meet to give 1 atom of A? Interesting. Interesting. Let's see. So we have 3 atoms of B. So 3 atoms of B combines to give you, fuse together to give 1 atom of A. Question is, what is the Q value? I just told you Q value is the binding energy of the product minus binding energy of the reactant. Here, what is the product? What is the reactant? Obviously, this is your product. This is your reactant. So, for the product, the binding energy will be EA, correct? It's EA, that's the product, minus binding energy of the reactant, that's EB, but there are 3 of them, so put 3 times. That's all. Do I have the answer? Yes, perfect. Amazing, guys. Very good, Sampath, Madhumita, Prem, Varsha, Deva. Come on, guys, I want to see all your names. I want to get to know you, and the more you answer and more you attend my classes, I think the name will get stuck in my memory. And others will also know you. And I will remember you when you meet me during the felicitation function. Like, oh, sir, I am Salva Kumari. Sir, I am Sampath. Sir, I am Chandana. Sir, I am Dharni. Sir, I am Murshida. Sir, I am Reena. Sir, I am Diva. Sir, I am Varsha. Sir, I am Prem. Sir, you remember I used to answer this. Sir, I told this dialogue in your chat box. And I would love to meet you guys during felicitation. You are going to become doctors, right? Or maybe someday I'll meet you somewhere in your clinic. Someday, obviously you will have a clinic or maybe a hospital, or you will be a scientist or maybe a researcher, or maybe you will teach the medical students something, and I would love to meet you guys. That will be amazing, and I will remember your names then. Alright, now let's go to the radioactive decay. Like I told you, sometimes you need to force somebody into some reaction. Like in the animations which I showed you, you had to throw 1 neutron, it hits the nucleus and then it disintegrates. It was a forced reaction. It was not natural. But there are some people or some nuclei where they automatically split. You don't need a trigger. You don't need any reason. They'll just split, or they'll just, undergo some reaction. That is a radioactive element. So a radioactive element like uranium-238 will split into smaller particles on its own. It does not need trigger. Thank you, Sri Harsha, means a lot. Just like I am giving you guys free education over here on YouTube. I'm so glad, bacha. Thank you so much. Means a lot. Yes, I'll post my weekly schedule. Yes, acing. Last week, like I said, I was not in town. That's why I was not sure how many lectures I would be able to take. So right now I'm back. So don't worry, I'll give you the schedule. Okay. That is a nuclear reaction. So which is radioactive, means it happens naturally, and there is a law of radioactivity. There is a law, and let's have a look at it. Just imagine this is a radioactive sample. This is a radioactive sample. It has many radioactive nuclei. It has many radioactive nuclei present in it. So let's say n number of radioactive nuclei are present in it. What happens is it emits radiation, it starts decaying, it basically decays, and let's say in time dt, in some small time interval dt, few nuclei decay, they decompose, rest of them are fine, intact. Okay, so rest of them are maybe fine. So these yellow ones, those are the still active nuclei. They are not yet split. but few of them maybe over here, okay, few of them they got decayed. So this is basically decayed. How much will decay? In dt time, obviously dn will decay, like how your tooth decays, some black thing is there, it has decayed, rest of it is white. So this is that white part, that yellow one over here is that undecayed part, so that is still active. So still active, still radioactive, I mean, is n minus dn. Everybody agrees to this statement? Exactly, it's going to be first order kinetics, you will see that. Oh, yep. I hope too, Selva Kumari, I don't fall sick. Okay, so next point over here is that in time dt, it decayed by dn. Then the law of radioactivity states that, where did it go? That the number of nuclei, forget this, decaying per unit time is proportional to the active nuclei in the sample. The number of nuclei undergoing decay per unit time is proportional to the active nuclei in the sample. What it means is that this one, dn by dt, dn, which is the nuclei which are decaying per unit time, is proportional to the nuclei present in the sample, that means proportional to n. This constant of proportionality, oh by the way I should put a minus sign. Why do I put a minus sign? Because it's decaying. dn will be a negative number because the change of the number will be negative, it's becoming less. So obviously it's negative, so to make it positive I put up minus sign over here, because dn is negative, minus into minus will make it plus positive. So for constant of proportionality is lambda, and this is basically n over here. This is the important formula, guys, which you should know. Minus dn by dt is lambda n, where this lambda is just called as the decay constant, and it completely depends on the nucleus, like uranium will have some lambda, thorium some other lambda, carbon 14 some other lambda. It depends on that nucleus. Obviously it's a materialistic property, it is a decay constant. So this might have reminded you of first order kinetics equation which you have studied in chemistry. Is that right? Very good, excellent. Okay. Will I take 11th classes lectures also? Yes. But first priority to 12th and then to 11th, because the exams are very close by. So important topics of 12th first, and then I'll do the important topics of 11th, and after the boards the remaining things, whatever, how much ever we can do, I will do. Okay. I'm not guaranteeing you I'll do all the topics, because I don't want to make fake promises, but I'll try to do as much as possible, but in the order of priority and weightage. That is very important. If I do sequentially chapter 1, 2, 3, it's of no use because time is less. You have to think about what is coming ahead. All right. Now I've put up all these things in the slides also. Let's talk about activity now. What is activity? Activity is nothing but, where did it go? Yes. Activity is nothing but how many disintegrations are happening per unit time. It's basically the disintegrations per unit time. Basically, activity is nothing but dn by dt's value, modulus of that, or just put a minus sign. How many nuclei are decaying per unit time is just the activity. That's all. Simple, nothing else. So this is another thing which you must definitely know. Now there is one very interesting thing about how much element or how much sample is left after some time. There is a small derivation for that. I'll just give you the important steps out of it. Like we all know, minus dn by dt is equal to lambda into n. I want to find how many nuclei are left after I wait for some time. So I don't want this derivative, I want to get rid of it. Most likely I will do integration, so bring that n over here. So minus dn by n is equal to lambda into t, correct? That's the formula. Very nice. Now I can see maybe, lambda into dt. Now I think I can do some integration over here. Yes, I can also shift that minus sign on the other side. It will be better, I feel. So I can put integration dn by n is equal to minus lambda constant integral of dt. Like, okay, fine, great. What are the limits, sir? Well, when time is 0, that means initially, there is n naught number of nuclei which are present initially. After you wait for some time, the sample left is n. So these become the limits. It should be corresponding. When this, then this. When that, then this. That's, yeah. Okay. You integrate it. So after integration, that part I leave it up to you. You can do it very easily. The final answer comes out to be n is equal to n naught original into e to the power minus lambda t. This is the formula. Again, obviously, you are supposed to remember this formula. And guess what? You can also write a similar formula for activity. So final activity is original activity e to the power negative lambda t. E is that exponent, 2.7. Okay. So standard values. So both are important formulas, both for activity as well as the sample which is left. So n naught is initial sample, initial number of nuclei, n is after time t. That's what it stands for. Exactly. So disintegration is infinite. Actually, if you wait for a very long time only, then you will get no disintegrations further. So the disintegration keeps on happening for a very long time. I'll show you the graph in a bit. Okay, I have put up all these things over here, the units also of disintegration and all that I have put. You can watch that later on in the PDF. That is not important. Let's solve some question, and again I'll come to some remaining parts, which is half-life and all of that. A sample has some disintegration rate of 5000. Okay, initially. After 5 minutes, you find it reduces to 1250 per minute. What is the decay constant? Interesting. Okay, let's do this. Guys, quickly think and tell me, what are these values? 1250, 5000. Are they number or activity? Are they number or activity? Think disintegrations per unit time. It's obviously activity. So what is activity and what is initial activity? Put it up in the chat box. What is A and what is A naught? Oh, no, Satya, the A value does not come out to be equal to N. So this happens when you substitute all of that. So A is not N. Don't think like that. Sir, you replaced N with A and N naught with A naught. No. Actually speaking over here, A is nothing but dN by dt. Okay, and this over here is dN naught by dt. They are completely different things, two different things. Okay, so please don't say A is N and A naught is N naught. It looks like that, but there is a derivation for that. Okay, don't get confused. Okay, oops, I think by mistake I showed the answer. Anyways, yes, so this is obviously A is nothing but 1250. Original activity was 5000 and the time is 5 minutes, and the question says decay constant, that means how much is lambda. Which formula will I use? Yes, Selva, I know I showed the answer, so maybe. So the formula that I will use is A is equal to A naught e to the power minus lambda t. A is 1250, A naught 5000, E as it is, lambda as it is, time 5. 0, 0 cancels. 125 by 500 is e raised to minus 5 lambda. I can bring that negative power below. It will become e raised to plus 5 lambda. 120 and 500 goes 4 times. 125 into 4 is 500. Flip this or cross multiply. It will become e raised to 5 lambda is equal to 4. Use logarithms. So log of 4 to the base e is 5 lambda. Log of 4, I can further write it as log of 2 square to the base e is equal to 5 lambda. Correct? Now bring that 2 outside. That's the formula of logarithms. Bring that 2 outside. So it will just become 2 log 2 to the base e is equal to 5 lambda. So lambda will be, bring 5 down. So 2 by 5 log 2 to the base e. Now 2 by 5 is 0.4. Log anything to the base e is ln. Ln is the shortcut for writing log to the base e. So 0.4 ln 2, which is option A, of course. That's right. Perfect. Everybody with me? Understood? So you need to know a little bit of logs. What are the different things of log that I have used? So guys, you know, log of x to the base b, if it is y, that means b raised to y is equal to x. So from this to this or this to this transformation you should know. So from this to this I have used here. And here I have used log of x raised to m is m times log of x. That is another formula that I have used over here. So this is this and this is over here. Alright, cool, very crucial. Now let's talk about half-life. Half-life. Some people you might have heard them saying, obviously none of your friends will say that, but midlife crisis. Okay, something like that. So anyways, so let's talk about what is this half-life. Now we all know, let me just draw the graph first. Okay, so we all know that the equation of the radioactive sample left after any time is given by n is equal to n naught e to the power minus lambda t, correct? That's the equation. If you draw this on n versus time graph, the graph looks somewhat like this. After a very long time, the sample becomes very small. When time value is 0, this value will be n naught. This value will be n naught. If you give me any time, at this time, what is the value of n? So I can get it graphically also or via the equation. So that is a graph of the sample present after any amount of time. Exponentially decaying graph. So it's also called as exponential decay. Exponential decay graph. Exponential because e power, decay because it is reducing. Now, if I ask you, at what time will the sample become half? So basically, when will it become n naught by 2? That time is called as the half-life of that sample, and that half-life is ln2 by lambda. Very important formula. ln2 by lambda is the half-life of any radioactive element. As simple as that. Yes, you can put the value of log of 2 as 0.69 approximately. That can simplify your calculations as well. Okay, bacha log, everybody clear about this? Very good. Now there is another thing which you would have heard, and that is basically average life. And you would have wondered, what is this average life? Okay, I'll tell you what is this average life. Imagine that you have a radioactive sample and it has radioactive elements. One of the element stays alive for some time and then it decays over here. It is alive, meaning it is basically active. It is active or it is alive. Another element stays alive only for this much time and it decays. Another element stays alive for a very long time and decays. Another atom stays alive for decent time and decays. So every element will stay alive for some time and then it decays. It's just like average life expectancy, mean life. So that is what average life is. So the average life is the time for which it stays alive. The second element, how much time it stays alive. You add all of them for all the elements present and divide it by n. That will give you the average life. Now this average life turns out to be just 1 by lambda. So that calculation part is not there for you. Don't worry. But main thing is there is no log 2. If you put log 2, what will it become? Average life? No, half-life. So if you put log 2 on the top, it will become half-life. If there is no log 2, if it is just 1 by lambda, it becomes average life. Okay? Clear? Understood? Very good. Let's do a question based on this. The half-life of a sample which has 1/32th of the original mass left after 60 days is how much? After 60 days, only 1/32th is left. What is the half-life of that sample? Come on, my warriors, figure this out a bit. What is the answer for this question? Well, if I give you the logic behind this, if the original mass was m, then after the first half-life, m by 2 will be left. Correct? After one more half-life, that means the second half-life, half of m by 2 will be left. After the third half-life, m by 2 into 1 by 2 into half of that is what is left. So like this, if you keep doing it, and after nth half-life, how much will be left? If it is asked, it will be m, and here you will have 2 raised to n. Correct, guys? M by 2 raised to n, that much will be left. Here 1/32th is left. That means 1 by 32 is 1 by 2 raised to n. Is that right, guys? 1 by 32 is 1 by 2 raised to n. Correcto? Great. So 32 is 2 raised to n. Therefore n is equal to 5. 2 into 2 into 2, 5 times is 32. So basically 5 half lives give you 60 days. So 1 half life will be how much? 60 by 5. 5 lives, 60 days. 1 life, 60 by 5 days. So that is 12 days of course. That's the answer. Simple logic. Option A, of course. Yes. Perfect. Many of you got the correct answer. Very nice, Avya. Prem Kumar. Oh, Prem, I think you said 5 for some other thing. Yes. Very good, Ajay. Very good, Sampath. Awesomeness, guys. Now, the entire PDF will be available on the Telegram channel. Make sure you join the Telegram channel, and also the link for the crash courses are there below. Let me show you what are the important things that you need to check out while you're watching the video, guys. If you go down, right, and I hope you have smashed the like button, guys. Yep. You can see this is the link of the Telegram channel. Hit on this link. Okay. That will open up the Telegram channel. I'll give you the PDF, everything. Okay. The notes. This is the test series. Some people only want test series. There you go, test series, guys. It's at 1,245 and you'll get 15 part tests, 10 full syllabus tests. You can learn how to improve your calculations, time, speed, etc. You'll get a detailed report card as well. So this test series is also available for all of you. The third link is basically the crash course for both 12th as well as droppers. You can see Crash is also there, Crash Plus is also there, with live classes and doubt solving. Test series is also a part of it, study material, assignments, notes. You can get it for 7,400 for Crash and 22,000 for Crash Plus with personal teachers, live classes as well. So these are the important things that you should note and enroll yourself so that you can put in the best and give in your 100%. Okay. Also, let me tell you guys, as you are watching this video over here, if you go on the channel, you can get our previous, your previous videos. You just go down over here. You can see physics crash course, right? All my lectures are there in this particular playlist. Right now, I've just started with modern physics. So you can see this is the modern physics playlist. Okay. I started with dual nature, atomic physics. This is a problem solving session. This is the theory class. There will be one more class. Tomorrow at 9 o'clock, I'll be taking class on semiconductors, electronic devices. And after that, there will be a class on just you will have for problem solving. Okay. That's what we are going to do. All right, guys. So I'm pretty sure you guys have had an amazing time today and you guys enjoyed the class. So formula sheet will be given to you in the PDF. So whatever you learned today, whatever I wrote, that's why I kept theory classes separate, so that you will just get the formulas and concepts. So use that and delete all the unnecessary slides, or just take printout of only necessary slides. Okay, seen it all live. Very good, very good. Thank you, Shafika. Thank you, Selva Kumari. Thank you, Hamshini. Thank you so much. Thank you so much. Oh yes, I was reminding you about a story and all that. So it so happened that I happened to go to Hyderabad and I visited one of the best facilities for eye care. And what is the best eye care facility, guys, for eye care? Do you know that? The college? Yes, it's LV Prasad Eye Institute, right? I happened to go there, and believe me, there were IIT Hyderabad, IIT Chennai students studying over there. Yes, there were IIT Chennai, Hyderabad students there, and the doctors were doing their research in IIT Bombay. It's like a collab over there, and they are doing amazing things, guys. Like, doctors, imagine doing artificial intelligence, machine learning, computer science, and engineers learning about, what are the different medical aspects of an eye. So there is a team build up. They are working together on doing robotic surgeries of eyes without the doctor present over there. And the patient just goes and sits, scans his eye, that's it. Detected, no need of doctor only. There is an algorithm written over there. The diagnosis is done. And then there is a robotic arm which comes and it does all the things. Crazy amount of, collaboration is happening these days. So that's why, what is the learning from this observation is that, please don't think that, okay, sir, I'm going to do medical, so I just have to know biology. That's wrong. Those are the kids or those are the students who just reach barely average level in life. Students are like, okay, I have to do biology well, but I have to also learn other things because I will need it at some point of life. You never know. You never know. Yes, just like Neuralink. So, students who think a little bit differently, I will never question, okay, why I have to learn maths? Why I have to learn physics? Why I have to learn history? I'm just going to focus on what I want. Arey, you don't know what you want, what you're going to become. So many things are going to happen. So, when you think of other perspectives, when you think that, okay, I need all kinds of knowledge, that's when you will be above average. So that's my message, and that's what you should also learn, because I have seen the other side. And it's amazing, these doctors wearing coat and entering IIT. Imagine. You will be also doing someday. That day, if you say, sir, I'm poor at math. Oh my God, what is this computer? I don't know this coding and all that. Okay, another guy will come. That's all. So yes, that's crazy. That's what is going to happen in the future, guys. And I hope you had a great lesson to learn and you enjoyed the class too. Keep it up, guys. Keep commenting after the session is over. Sir, watched it. Done. I know how many of you watched it, because many of you will be watching the recording. How do I know? So guys, put it up. Even if I watch it live. Sir, done. This is done. I've read this. NCRT done. PYQ done. This is done. Put up whatever is your achievement. Put it up in the comments. You have to do that. Okay. Bye bye, guys. Have a great time. Wonderful time. This is Captain Shreyas signing off. Hasta la vista.